we've done these kinds of problems before, so we haven't done very much work by the way of kinematics here. It's the same stuff, except that instead of displacement, we'll have angular displacement. Instead of initial velocity, we have angular velocity. Instead of final velocity, we have final angular velocity. And we'll have angular acceleration and time. And yes, 4 of these are vectors. So you told me it took 12.2 seconds to do this. What other information did I give you about this? What was it? All right, so we started from rest. Did I give you any other information? How many rotations did it make? So I told you the angular displacement because it made 6 rotations. Excellent. That's 3 pieces of information. You should be able to tell me how fast it was going when it made it to the end and what the angular acceleration was. I'd like this one in RPM, and I like this one in radians per second squared. And I'm just interested to see if you can do this. So try. I'm going to put some information on here that might help you, and I'm going to talk it out because some of you have requested that I give you more steps and more guidance. I don't really want to do this, but I'm going to do so anyways. But most of you should be able to do this on your own. Before you get started, though, you should decide whether you're going to convert from the beginning or convert at the end. I'll say that you must be in consistent units. To use a motion equation. Now, then choose your motion equation and solve for your answer. Then make sure your answer is in the right units. So, since we have some folks need help, let's get rid of the answers. I'll point out at the start of the problem that I have 5 motion variables and 3 pieces of information have been given to me or I was able to measure. So let's start with the final angular velocity, which needs to be in rotations per minute. I need to choose a relationship that has all of those things in it except for acceleration, since I don't have it. I'm going to choose delta theta equals 1/2 omega final plus omega initial times t. Again, step 1, choose a relationship that has the 4 pieces you're looking for in it. 3 will be given, 1 will be an unknown. This is not really an additional step. You had to do this before, but you can only work in 1 unit at a time. So it's either all rotations or all radians, and all minutes or all seconds. You pick. Now right now my angular displacement is in rotations, and I want my velocity to be in rotations as well. But my time is in seconds. So I either convert to minutes now, or I convert to minutes later. I'm going to choose to convert to minutes later, and I'm going to work with the units I have right now. So 6 rotations equals 1/2 omega final plus 0 times 12.2 seconds. Now, when I find the final velocity, it'll be 6 times 2 divided by 12.2. It'll give me that omega final is 0.9836, and this is rotations per second. Now, this for some of you could be a super simple conversion. For some of you, it might be a hard conversion. I'm going to assume that some of you really need to see the next part explicitly. I'm going to convert this from rotations per second to rotations per minute using unit multipliers. It's a little heavy-handed for this, but they're not all going to be this simple. I start by writing out what I have as a fraction. And I write out the units I want it to be. I'm sorry, this is seconds. Yeah, I'll write out what I want it to be. Give myself some space to work. I'm going to use unit multipliers, and I'll use however many I need to get from what I have to what I need. Now, rotations is going to stay, so I don't have to convert it, but seconds is going to be converted. So that's the only one I have to work on. And I happen to know the conversion from seconds to minutes, so I think I can do this in one step. If it was like seconds to hours, I might have to do this in 2 steps, right? Because I don't know the conversion from seconds to hours. I know seconds to minutes and minutes to hours. So really, it depends on what conversion facts you know. But I know seconds to minutes. So I want to cancel out seconds. They're in the denominator, so I write seconds in the numerator. I want to be left in minutes, so I put minutes in the denominator. Somebody said, this is just like stoichiometry. Yes, because stoichiometry was just conversions. Now, I know that for every 1 minute, there are 60 seconds. When I do this, seconds will cancel out, and I'll be left with rotations per minute. So I just need to multiply my number by 60, and I get 59 rotations per minute. Everybody good there? Any questions about that? Alrighty. So we go and do the next one. So get rid of this. And if you'll remember, I tend to treat problems from scratch when I start back over again. I try not to reuse stuff if I don't have to in case I made a mistake. So I want a relationship that has everything in it, but I'm going to exclude that I know what the final velocity is. And I think I'll use delta theta equals 1/2 alpha t squared plus omega I times t. Time is in seconds, and delta theta is in rotations. If I work this out, my answer is probably going to be in rotations per second squared. So I can decide to either convert at the start or convert at the end. Last time I converted at the end. So I think this time I'll convert at the start. I'm going to convert rotations to radians. I'm going to use a unit conversion here with rotations on the bottom and radians on the top. I have a rotation fact for this. For every 1 rotation, there are 2 pi radians. So I'll take my 6 times 2 times 3.14159, and I get 37.7. That's radians per second. Now, hear me out, guys. You guys do weird stuff when it comes to pi. For whatever reason, it makes you crazy. In your head, just make pi 3. It'll help. If pi is 3, 2 pi is 6. How often does 2 pi show up in stuff like this? I mean, it's going to be all the time, right? So you're always multiplying or dividing by 6. Estimate your answer ahead of time, because you guys are going to make mistakes here. I can prove it in just a minute. So just in your head, always estimate out. I was going from rotations to radians. I'm multiplying by 6. I should add a number in the 30s. I do. So going back to do the problem, though, 37.7 equals 1/2 times alpha t squared, 12.2 squared plus 0. So I'm just multiplying by 2 and dividing by 12.2 squared. And that's where I get alpha equals 0.51, and that's already been converted to radians per second squared. Now, I have a small aside for us, but are we all good for this? Could you convert this to radians per minute squared? Actually, let's go all the way with it. Could you convert this to rotations per minute squared? Do you know how to do that? Bless you, this would be 2 conversions at once. Can you take 0.51 radians per second squared and convert it to rotations per minute squared? If you don't think you can, you should raise your hand now and say, no, I don't think I can do it. If you think you can do it, you should try. Okay, so let's do this together. I'm going to say a set of steps, and I will be very careful. You should write the set of steps down if you don't know how to do it. I'm going to start by writing this as a fraction. So this will be radians per second squared. Now I have to do 2 conversions. I have to convert the radians and I have to convert the seconds. So that means 2 unit conversions. Now, it doesn't matter the order that I put these in. So, because you can multiply in any order. So I'm going to start with the radians. And I want to get rid of radians, so I put radians on the opposite side. So step 1, write your value as a fraction. Step 2, write what you want to transform it to. Step 3, consider the number of conversions. Create a fraction for each one. Again, consider the number of conversions and create a fraction for each one. Then, start with your first conversion. Put what you have on the opposite side of the fraction. And put where you're going on the opposite side of the fraction. So I put radians on the bottom, I'm going to put rotations on the top. Then write in your conversion fact. 1 rotation is 2 pi radians. I have seconds. It's on the bottom, so I'm going to put seconds on the top. I want to be left in minutes. I'll put minutes on the bottom. I'm going to write in my conversion fact. For every 1 minute, there's 60 seconds. However, am I actually converting from seconds to minutes? What am I really converting? Seconds squared to minutes squared. If you have a unit that you're converting that is a square or a cube, you just square or cube your multiplier. This will come in really handy when we get to fluids at the end of the year. So now it's going to be 60 squared that I'm using as my conversion fact. And I'm going to do an intermediate step. I'm going to write out the fraction. It's going to be 0.51 times 60 squared divided by 2 pi. My answer will now be in, cancel the radians with the radians, and the second squared to second squared, and I'll get rotations per minute squared. Now this is my answer, but you guys make a mistake here, And we're going to see if you make the mistake now. Typed into your calculator 0.51 times, whatever that little symbol is, 60 squared divided by 2 pi. And your calculator did exactly what you asked. It multiplied, it took this number, multiplied by the square of that number. It understands that it has to square it first, then multiplied. Then it divided by 2, and then it multiplied by pi. But it had to divide by pi, because both 2 and pi are in the denominator. So if you want to use your calculator and type it all in together, you need to tell it that both of those are in the denominator, or you have to do divided by 2 divided by pi, because it does order of operations. It doesn't know that both are supposed to be in the denominator. Now, hear me out. If you want to not get these wrong and not have me call you out, before you do your answer, just do this. You won't get the right answer. You'll get close, though, real close. I mean, notice these are off by almost a power of 10. Right? Big difference. So try doing 6 and then do your 2 pi, just to make sure you know what the ballpark of your answer is going to be. It will help, or continue to make this mistake. But let's not continue to make this mistake if we can avoid it. We've done enough where you should be able to do these now. Like, we've had enough practice. So we're going to practice one more time, but this time it's for all the marbles. Like, I don't want to have to do a bunch of this. I'm going to give you homework like this so that you can practice, and there'll be all sorts of motion equation problems. They're going to have all the conversions, all the same stuff. But let's see if now that we've done one together, if you guys can do this on your own. 3. And what was delta theta this time? 6. And our initial velocity still 0? Yep. All right. Try it again. I want RPM for omega final and radians per second squared for angular acceleration. So the table, about 1.5 rotations, it took the wheel 1.5 rotations to get across the table. So I placed the wheel here, and then we rolled the wheel across the table. And when the wheel got here, the tape was almost back to the very top. And it took 1.5 rotations to get there. Now, you know things. 1.5 rotations means the wheel traveled how many circumferences? Good job, 1.5 circumferences. Right, and went one full circumference, then another half circumference. How do you calculate circumference? 2 pi r. So if I take this and multiply by 2 pi r, I will get how far this goes, right? So tell me the distance. Now, before you do that, you know you can multiply in any order, right? Do you guys know that you can do that? So if I regroup this, I get 1.5 rotations times 2 pi times r. You guys are smart. I'm trying to teach you something. You may not see it now, but you know something about 2 pi. We've been using it already today. What is the conversion from rotations to radians? So this is actually taking our rotations and converting it to radians. You guys see that? Times r. Because this is how you go from linear coordinates to angular coordinates. You just multiply by the radius. But you have to be in radians to do so. This is a must. So this, for us, was 1.5 rotations. If I want to find the length of the table, I need to convert that to radians first, then multiply by the radius, which I'm assuming you guys are doing right now. All right, so meter sticks right here. 1 meter, 2 meters, 75 centimeters. Now what'd you guys get, like 2.8? Why wasn't it 2.8? Did the tape make it all the way back to the top? No, so it's just a little less than 1.5 rotations. You guys see it? Now, the truth is, and this is important, if you're going to write anything down that's important today, make sure you get this, that all of them are like this. These represent the rotation of an object. These represent how far it rolls. I wrote it fast. It's either how far something rolls if it's rolling, or it's how far a point on the object moves, or how fast a point on the object is moving. But these have to be in radians. If they're not in radians, this doesn't work. This is how we move from something angular to something linear. It just involves the radius. The answer over here will take the units of the radius. So if the radius is in centimeters, the answer will be in centimeters. If the radius is in meters, the answer will be meters. Now, we're going to practice this a little bit, but I want to emphasize again, and I want to be really clear about it. This object has one rotational speed, right? One rotational speed. Is it clear the green tape is moving twice as fast as the blue tape? And the blue tape is halfway to where the green tape is. So since the radius is twice as big for the green tape, it's moving twice as fast. It's just a direct proportion. Welcome to pack up for the day.